Problem number 9. A small bead is placed on the top of a frictionless glass sphere of diameter d as shown. The bead is given a slight push and starts sliding down along the sphere. Find the speed v of the bead at the point at which the bead leaves the sphere. Solution for problem 9. First, let's draw the free body diagram. When bead moves by angle theta, we have two forces acting on it. That's normal force and force of gravity mg. And we can find what is the force in n direction acting on this bead. Because this bead is moving by circular motion, we have normal acceleration equal v square over r, and that's equal to net force from normal force and mg. We have mv square over r equal mg cosine theta, which is a projection of mg on this direction, minus normal force. And the condition for bead to leave this sphere is when normal force equals 0. And now mv square over r equal mg cosine theta, m is cancelled, and v square equal r g cosine theta. So we have to find what is the relation between cosine theta and v square. This we can find from energy conservation, because the difference in potential energy equal to kinetic energy. 1/2 mv square equal mgr multiplied by 1 minus cosine theta. This is our energy conservation. Now we can find what is cosine theta by equalizing this v square and this v square. That will be this equation, and cosine theta equal 2 over 3. It means that v square equal 2 over 3 gr. And finally v equal square root from gd over 3, which is answer E. That was solution for problem number 9. Problem number 10. Two blocks are suspended by two massless elastic strings to the ceiling as shown in the figure. The masses of the upper and lower block are m1 equal 2 kg and m2 equal 4 kg respectively. If the upper string is suddenly cut just above the top block, what are the accelerations of the two blocks at the moment when the top block begins to fall? Solution for problem number 10. First, let's write the free body diagram. If we have tension T1 in upper string and tension T2 in lower string, and we have force of gravity on M1, it's M1G, and on M2, M2G, so we have two equations for static equilibrium. We have T1 equal M1G plus T2, and the T2 equal M2G, and T1 equal 60 newtons and T2 equal 40 newtons. When we cut upper string, immediately after that T2 is still 40 newtons, and we have other equations. So M1 A1 equal M1G plus T2, and M2 A2 equal Mg minus T2. We see that M2G equal T2, so that's equal 0. M1 A1 equal 60 newtons and M2 A2 equal 0. From here we can find that A1 equal 30 meters per second and A2 equal 0. That's the answer D, which is correct. That was a solution for problem number 10. Problem number 11. The power output from a certain experimental car designed to be shaped like a cube is proportional to the mass m of the car. The force of air friction on the car is proportional to AV square, where V is the speed of the car and A the cross-sectional area. On a level surface, the car has the maximum speed V maximum. Assuming that all versions of this design have the same density, then which of the following is true? To which expression Vmax proportional? First, we have a power equal force multiplied by velocity, and power proportional to mass, and force proportional to AV square. So we can write down mass proportional to AV cube, and because cross-sectional area proportional to mass power 2/3, we have this proportionality, and from here we have mass power 1/3 proportional to V cube, and V proportional to m power 1/9, which is answer A. That was solution for problem number 11.